you very much. First and foremost, I'd like to thank the organizers for inviting me here to speak at this wonderful conference. It's a very nice place to be. I've met many old friends and even met collaborators that have only spoken through Skype, on audio, and I finally get to meet them. Okay, so today I'll talk about, we've had a few talks today on M5-branes, 2.0 theories. We've had talks on self-growth strings, and now I'm going to talk about little strings, and a little bit more about the M5-brane world volume theory. So we're going beyond 2.0. We can still say something about it, as I'll show you now. So the title of my talk will be From Little Strings to M5-branes, and we're going to use this very interesting sigma model. It's a quasi-topological sigma model, which means that it is not fully topological. Its stress tensor is only trivial in the anti-polymorphic components, but it's not trivial in the polymorphic components. It's still scale invariant, so we still have a conformal theory, and so we still have some state operator correspondence. And now we have this very interesting target space. It's a loop group, and as I'll explain, this would allow us to understand the excited states of the little string. The non-excited states of the little string would give you the ground states would just give you the 2.0 tensor multiplet. The particle limit of this little string would just give you the 2.0 from the field theory. And if you look at the excited states of the little string, the half excited states of the little string, that gives you something that goes beyond. And it goes beyond. Okay, and then we'll say something about the EPS sector of the M5-branes using these little strings. Okay, so the outline of my talk will be as such. I'll give you some introduction and motivation for why we're studying this. And then a gong show, that's what Neil said, what this talk is about. So in case you get lost along the way, you'll know what to look out for. And then we'll go to the main body of the talk where I'll explain the details, to some extent, of details of how we got those results. And then I will conclude and offer some future directions that we can work on and think about. Okay. So, introduction. So in this talk, we'll discuss, as I said, a quasi-topological twist of the 2D n=2,2 nonlinear sigma model with worldsheet CP1 and target space, the base loop group S2K. Okay. So the reason or the motivation for doing so is that we would be able to use this sigma model to describe, as I mentioned, the ground and half excited states of the 6D AK-1 and 2.0 little string theory. That's the string theory that lives, say, in an NS5-brane in type 2A. We have fundamental strings that are bound to the world volume of the NS5-brane, and when the coupling goes to 0, the string coupling goes to 0, and so gravitational modes decouple. So you don't have a theory of gravity within the NS5-branes. Okay, but you have a finite string length, so you still see stringing effects in the NS5-brane world volume. So this is the little string theory that we're talking about. So it's AK-1, so you could think of it as regular just NS5-branes, no orientifolds. And if you add in orientifolds, you could change this to something else, like the D group, special orthogonal groups. So we'll be studying just the NS5-brane with little strings inside. And that's one motivation. The other motivation, which is mathematical, so I figured that the audience is a good mix of people from math, people from physics. So for those of you from math, we would be able to provide a physical derivation and generalization of a math relation by Braverman and Finkelberg, which defines the geometric Langlands correspondence for surfaces. Okay, so this is in some sense, extension of the usual geometric Langlands correspondence for complex curves. So regular geometric Langlands involves G bundles on a Riemann surface, and that's a complex curve on one side. And then on the other side, you have these things called D modules. So these two guys, they decided to generalize the story with the data putting in as complex surfaces, not complex curves. And what happens when you do that, mathematically, the correspondence becomes as such. You have these cohomology classes on the moduli space of instantons on R4 on one side, G instantons on R4 on one side, and on the other side of the correspondence, you have an affine algebra of Langlands dual G. Okay, so the correspondence for complex surfaces becomes this statement. All right, so we'll be able to prove this and generalize this to beyond just cohomology classes on the moduli space of instantons, but generalize this to check cohomology classes of chiral differential operators. I'll explain what that means. Okay, it's just a sheaf of beta gamma systems whose check cohomology would help you to describe the half-twisted string or the quasi-topological string that we are going to explain. Okay? So it's, in some sense, you could think of it as a higher conformal dimension extension of Durham cohomology. So if you look at cohomology class, a differential form, so if you define things which in dimension 0 just goes down to Durham cohomology, then you have an extension of dimension non-zero that gives you the chiral Durham complex. I'll explain that in detail. And then the third motivation is, of course, to understand the half and polar BDS sectors of the M5-brane world volume theory. So you know there exists a 2,0 supersymmetry in the M5-brane world volume theory. And from this supersymmetry algebra, you can see where you can have BGS states which saturate and energy bound from the supersymmetry algebra. And we are able to sort of understand a little bit of these BGS sectors through this model that describes this thing. Okay, so these are the motivations. So this talk is based on a paper that I wrote with my postdoc and students. One of them is here. Ashwin is. So if you have any questions, you can ask me or you can ask him. I'll be gone tomorrow, so you can ask him if you have any questions. Okay, so it's based on earlier insights in this work that I did. Okay, this is where this half-twisted model and its relationship to check cohomology of the sheaf of chiral differential operators first appeared. So you can think of this as like something that's in between the physical string and the topological string. Okay, so topological string just has ground states. The physical string has excited states both on the left side and the right side. And the quasi-topological sigma model, and therefore the quasi-topological string, only has excitations on the left side, but no excitations on the right side. Okay? So in some sense, you can define elliptic genus, because elliptic genus is really counting states which are excited on one side. Okay, so, and we will do something similar later on. So this is based on this, and that's the reason for working on a quasi-topological sigma model loop group, because of these properties. And then the other paper, okay, so this involves the relationship of M-theory dualities involving 5-branes, compactified on non-compact Calabi-Yau two-folds, essentially gravitational instantons, and using the dualities in M-theory to actually derive what Gablerman and Finkelberg did. So in two-dimensional geometric lambda duality, we mean two-dimensional complex surfaces, as opposed to a one-dimensional case of complex curves. Okay, so this is really geometric lambda duality for surfaces. So some of the insights for the second part of the derivation were from this paper here. And then the final part, where we want to describe the M5-brane world volume and the quarter and a half BDS sector states of the M5-brane world volume theory. Yeah, some of the insights came from here, and the references within. In the late 90s, there was a lot of work on DLCQ, discrete line quantization of the 5-brane world volume theory, and we're going to sort of rehash that, revisit that in the context of this guy here, using a theorem by Tia. It's a very, very nice theorem which allows us to connect some things which we wouldn't be able to connect otherwise, and I'll explain. Okay, so the gong show for this talk, okay, in case you miss out along the way, right? So the first result we'll get is this. So in the quasi-topological sigma model with target base group of S2K, okay, there is a scalar supercharge, okay, bar here, which generated supersymmetry survives on the CP1 worldsheet. Okay, it's a scalar, so it doesn't get broken on the worldsheet that's curved, whereby in the Q cohomology, so things which are annihilated by the Q charge, but are not written as Q times something else, okay, we have the following currents that generate the following toroidal current algebra. Okay, so these guys here, okay, so we have an OPE essentially, which you take the residue that will give you the commutator. So we have these fields, these currents. Now these currents are local operators, which are Q close but not Q exact. Okay, and so they generate this algebra here, and this is a toroidal algebra. So we will derive that. So just to give you a sort of a forward insight in how this is possible, because if you have a target space that is a loop group, you would have in its index, space-time index, its tangent vector index, an index which involves the algebra indices of the base, which is the G, the group, and then you have an index that tells you about the loops. Okay? So essentially, the fields in your sigma model would have two indices. There's a Lie algebra index and there's a loop index. And so when you construct fields or local operators of the theory, you would be able to get things which have two kinds of indices. Okay, the A here and then the N here, for example. Now the third one that you see here is just from the Lorentz expansion of the field. Okay, that comes even with your Virasoro algebra, you have your stress tensors, and then you expand them in terms of the LNs. That's one index already from the Lorentz expansion. But outside of the Lorentz expansion, you have a Lie algebra index that labels the base of this guy, and then the N here which labels the loop over this guy. Alright, so once you have a sigma model that is defined on a loop group, you would have fields that look like this, and naturally you would be able to find such relationships with current algebra. Okay? So we find this now in the topological subsector of the theory, which means in the ground state sector of the quasi-topological theory. So the quasi-topological theory, the spectrum is this. It's zero conformal dimension on the right side, but on the left side it has zero or more. But if you restrict even the left side to be of zero conformal dimension, you are in the topological sector. And as I mentioned just now, this check homology of Durham complex just becomes a usual Durham complex, and then you will have exactly the same observables as a topological sigma model. Now when we do that, it just means setting this guy here, which is the eigenvalue of the conformal dimension on the left side, to 0, and this guy here collapses to an affine algebra. Okay. Yeah?
Do you have some kind of symmetry exchanging the n on the n? So it looks pretty symmetrical.
Yeah. So yes, that's right. So yeah, it's symmetric in M1 plus M2. That's right. Yeah. It just comes out from the calculation. So
because these two circles are very different. One is the target space, the other.
Yeah. So this guy lives on the worksheet. This guy lives on the worksheet. So this guy lives on the worksheet. Yeah. See, these are lives on the worksheet. Yeah.
But is C1 equal to C2?
No, it's not.
So there's not.
That's right. C1 is not equal to C2. So it's not exactly symmetric in M1 and M2 then. Yeah, because you switch this around, it's not exactly the same. Yeah. Okay. Alright. Okay. So that's okay. So first two results in the Gong show. Third result in the Gong show. Okay. So now we use this theorem by Tia. So this theorem by Tia, a very nice theorem. It tells you that you can identify the moduli space of instantons on R4 with the moduli space of holomorphic maps from CP1 into the base loop group. Okay, it's a very nice paper. It's called Instantons in 2 and 4 dimensions. Okay, so there's an identity, a diffeomorphic identity between these two spaces. So because we can use that, it will mean this. We could describe this guy here. So we have this little string theory, and we work in the DLCQ framework. Okay, and the DLCQ factorization of this little string theory on R5,1, okay, can be related to a sigma model on the moduli space of instantons. And then you have this notion of the topological sector of this sigma model on the moduli space of instantons, giving you the Durham cohomology on the moduli space of instantons. And then likewise the half excited states of the little string of this little string theory, giving you the check cohomology on the moduli space of instantons. But using our Tia's theorem, we could map these observables to the other guy for the Durham cohomology on the space, the loop group space, the maps of CP1 of the loop group. And then we could also map the check cohomology of the Durham complex onto the space of maps from CP1 of the loop group. And so the latter is given by the modules of that algebra that we saw just now, because that's the loop group side. Okay? And And then the Durham cohomology on the space of instantons, that's from this side. Okay? And then likewise, in the topological sector, where it's the ground state, then we would have modules of the EFI instead. And then we have the ground spectrum of this guy given by this modules of EFI. And the next result, as we said, okay, so we have described the little string spectrum. So the next thing that we wanted to do was to derive and generalize Braverman and Finkelberg's result. Okay. So again, so on this side, that's from the sigma model on loop group. Okay, and it involves this affine algebra and the modules of this affine algebra. And at the same time, this part here is also, associated with the Q cohomology, which is given by the Durham cohomology on the space of maps. But that's met by Atiyah's theorem to the cohomology on the space of instantons on R4. So notice that this is intersection cohomology because, as what Xiaopin has mentioned, the space is singular. So to mathematically define such quantities, it's an intersection cohomology. But nevertheless, it's identifiable with the L-squared harmonic forms, which are then again identifiable with Durham cohomology. Okay? So this result that we have is exactly what Braverman and Finkelberg sort of proposed or conjectured. So in some sense, we have a physical verification of this mathematical result, okay, which shows us the utility of Atiyah's theorem and using the sigma model or loop group, the usefulness of these two things. And this as, in some sense, a mathematical verification, okay, if you will. And of course, we can go further. So now we know that this is true. So what can we say about the left-excited version? This is the topological version, the ground state. So from the left-excited version, we'll get this. Okay, so this is a toroidal SUK algebra. Modules of toroidal SUK algebra. And on this side, we no longer have just Durham cohomology, we have the check cohomology of this guy here. This is the sheaf that I was talking about. Okay, the sheaf of chiral-Durham complex. Okay, let me just explain this a little bit. So essentially, this is like, you could think of a sigma model with some target space, a local patch of the target space, and on that local patch of target space, you have what is called a beta-gamma BC system. So if you were to write the Lagrangian of the sigma model, where the target space is only a local part of the target space, it's written like beta del gamma plus B del C. You can write it as such. Okay? So essentially, this is actually a sheaf of a theory, conformal field theory. And to define the check cohomology of this guy, we need to do the usual gluing and the position functions and all those things. Okay, so that's technical, but I won't go through that. So all I can say for the physicist is that, of course, with the cohomology here, you have some degree. So if you have some operators with some values of Fermi fields inside, and this would count the number of Fermi fields inside, so that's roughly, you will see this more explicitly as we go on. So the point is, we have a generalization of what Braverman and Finkelberg has proposed as this. Okay, so you have a toroidal version of that on this side, and you have a check cohomology of the sheaf on the other side. So this is completely novel, it's something new, something for math people to think about and to try to derive or to prove. And finally, of course, we want to say something about the M5-brane. Okay, so when you use if you look at the supersymmetry algebras of the M5-brane volume theory, we can show that there's a correspondence between the ground states of the little string, that is, the states that are annihilated by all the supercharges on the whole sheaf of the little string, with the half BPS sector of the M5-brane volume theory. Okay, and how do you see that? That's because these little strings which are inside the branes, they are half BPS objects inside the whole volume. The supersymmetries of the ambient space, the 6-dimensional space, some of them get preserved on the whole sheet of the string. Okay, so they get inherited from the ambient space. Some are broken, half of it is broken. So you have 16 supercharges of the M5-brane volume theory. 8 of it is preserved on the whole sheet with 4 left and 4 right moving on the whole sheet. And if you look at states which are annihilated by the 4 left and 4 right, you are exactly looking at a certain BPS sector of the 6-dimensional whole volume theory. Okay. So this, we don't need a Lagrangian to say this because it's just from the supersymmetry algebra and the states from the algebra. Okay, and so that happens to be the ground states of the little string, and then we sum up these states, and these states are in the module of the affine algebra, if you remember. Okay, because we used Artia's theorem to map the things in the little string to the quasi-topological sigma model loop group, and that happens to be the modules of the affine algebra. We sum them up and we get this guy here. So this is actually like a character of an SUK affine algebra. Okay, and it behaves like a modular form, not exactly. Okay, you do the transformations, there are some anomalies here and some, but it transforms as a representation of SL2Z. So, I think earlier on, some people were asking, is there a way to actually see SL2Z in 2,0 theory? Okay, being inbuilt into it. Well, in some sense, this is it. Okay, so we're looking at the ground states of the little string. So if you look at the M5-brane itself, the ground states of the little string, that generates the 2,0 tensor multiplet in the particle limit. Okay, and so we do see an SL2Z symmetry that's coming out from this. Who would have thought, right? So we see this here. Now let's look at the quarter BPS. Okay, quarter BPS. So quarter BPS of the whole volume theory means annihilated by 4 supercharges out of the 16. And that 4 supercharges is inherited by the 4 left moving on the world sheet. So if you're looking at states that are annihilated by the 4 left moving on the world sheet, that would correspond to the quarter BPS of the 6D theory. And if you remember, that is the half-excited states of the little string, which is given by modules in the toroidal algebra of SUK, and then you sum up those states again, and very nicely you get something that looks like this. So it's almost an automorphic form, it's a cousin of an automorphic form, but it transforms as SO2,2Z. So you see a stringy sort of symmetry here now. So once you consider states that are excited, you get to see the stringy spectrum of the whole volume theory. So this, if you sort of look at it, it looks like T-duality. It's T-duality group. Okay? It's like you have 2 circles in the background. And why is that? So we're using BLCQ. So you come back to find one direction. Now if you compute the partition function, you're taking the end of time with the start of time and you're linking it together. So you see that there are actually 2 circles in some sense in the target space of the string, and the string detects this sort of circle in the target space, giving it some kind of T-duality symmetry. Okay, I'll say more about this and how it relates to the decompactified case in a while. But that's the Gong show. Okay, so this is the Gong show, so this is what we're going to do. Okay, so it's pretty systematic, and if you get lost along the way, this is what you should be looking out for. Okay? Right, so let's explain how we got these results. I'm sorry the slides are a bit too early, but I sort of wanted to keep it self-contained, so I tried to put essential data inside. So just a quick review of loop group. So loop group is basically, it consists of maps from S1 to J, and if we're talking about base loop group, then it has this additional constraint that if you parameterize the S1 by this guy here at 0 in maps, it becomes an identity map. Okay? And essentially, this base loop group is essentially just this loop group mod out by G. The key point is that this target space itself would have an LG action. Okay? Just like flat manifolds. Okay, like G over B, like the sphere. CP1 is the flat manifold, for example. That's the whole sheet, but in general, right? So you have a G action on a flat manifold, so it's something like this. Is, of course, this is not the Cartan, so it's, well, it just has an LG action, it's not a flat manifold. So the interesting thing is that it emits a closed, non-degenerate symplectic 2 form. So all this you can find in Siegel's loop groups. Okay, you can find it in Siegel's book. Okay, and the complex and the symplectic structures of the base loop group are compatible and conspire to make it a Kähler manifold. Okay. And so a bit more detail on the loop group. So if you let this zeta and eta be elements of the base loop algebra, then you can write it as such. Okay, so you can write it as such. So if you look at this guy here, so this TA here, that's the Lie algebra generator. So that generates the base manifold, which is the group. Okay. This guy here parameterizes the groups.
You mean summation, right?
Yeah, summation, sorry. Okay. Sorry.
It's Fourier series.
Yeah. Summation. Sorry. Yeah. Okay. So then this guy here, okay, which contracts both, you can think of it as the map. Okay, that's roughly the intuition. Okay, so the point is that this counts from 1 to dimension G, then this n here takes any integer value, and then the base point condition just goes to this, so we have a metric. So the point I'm trying to make here with all these details is this, that in the usual case, when you have a normal sigma model on a normal target space, then your metric itself only has like 2 distinct indices, but now we have 4. That's the point. Okay, you have a Lie algebra index and then the loop index. Okay, so so even if you look at this algebra here, so again, it's got not just A and B in the usual Lie algebra kind of way, it's got M and N, and then you have these. These are structure constants of the Lie algebra of SGK. Right? So with that in mind, we can write down the sigma model. Okay, in 2 dimensions. This is the usual n equals to 2, 2. We're not twisting it yet. So this is the 2, 2 sigma model that you can write. So there's some conditions on these guys. The reason for these conditions is because we are constructing a model on the base loop group of the real Lie algebra, SUK. So, and to get that, we start off with the complex one and then have a condition that reduces it to the real. Okay, so we need these conditions, but doesn't change anything. The form doesn't change. It just tells you that when you have negative integers for this expansion here, it's just the complex conjugate, and the form will look the same. And you just sum over all positive values of n. Okay? And so this here is the covariant derivative for the Fermi field, so it looks like the usual thing. Christoffel convection, del Z5, but then again, as I said, your indices, your space-time target space indices would have 2 types of indices. Not just 1, but 2 of them. Okay, so as you can see, it's all 2 of them. The form looks exactly the same as your usual sigma model on a regular target space. Now, so what we want to do is to twist this guy. Twist it in the sense of, what Wickham did, which is essentially to shift the Lorentz generator by the eigenvalue of the Lorentz generator, to redefine it, mix it with the vector R symmetry generator or the axial R symmetry generator in n equals to 2 supersymmetry algebra. You have 2 R symmetries, the axial one and the vector one. Okay, so depending on how you redefine the Lorentz generator using the axial or vector, you can A twist or B twist. So we want an A twist. So what happens is that out of the 4 supersymmetries on the worldsheet, 2 of them will become scalars because you're redefining the Lorentz generator, which means you're redefining the spin eigenvalues of these guys. And only the Fermi fields are charged, so only the Fermi fields have their spins redefined. Okay, so in particular, the superchargers, which were spin half, 2 of them will be shifted down to spin 0, 2 of them will be shifted up to spin 1. Okay, so when we do this twist, we end up having, we end up changing the spins of Fermi fields. So if you look at this Fermi field that appeared in the Lagrangian, it gets shifted, okay, it becomes a 0-1 form. So spin 1. Okay, holomorphic 0-1, anti-holomorphic 0-1 form. This guy becomes a scalar, this guy becomes a scalar. They're still Gaussian, meaning they still anti-commute, but they have spin 0. And then this guy here becomes 1, 0 holomorphic form on the ocean. Okay? And then the form of the Lagrangian looks the same, we're just replacing these fields with a different spin inside. Okay, and then notice that instead of 2 terms of del phi and del phi, we can write the second term as a pullback of this syntactic form on the target space. And so eventually we have this action here. Okay, so we can consider this the perturbative part, and this the non-perturbative part. This has got to do with pullbacks of the syntactic form, which is worldsheet asymptotes. Okay, so this is an integer number here. So these maps here, it's of integer degree n. Okay, so this is like standard stuff that you see in topological asigma models whereby you have Gromov-Witten invariants associated with these things here. So how is it quasi-topological? We have twisted both. I mean, we have twisted it in the usual A way, okay, where we have two scalar superchargers. So how is it quasi-topological and not topological? Okay, so you look at the supersymmetry transformations of each of the scalar supercharge. Okay, let's just look at one of them. So we have two superchargers that are scalars. Okay, as I said, out of 4 superchargers, 2 are scalars, 2 are vectors. So the 2 that are scalars are, the 2 that are scalars, this guy and this guy. Let's look at the transformations that are generated by this guy on the fields. So they look like this. Okay, and because you have twisted the theory such that this is a scalar supercharge, its parameter here is also a scalar Grassmannian parameter. Okay, and if you look at it, the fields all match in terms of dimensions. This supersymmetry relation is 0 dimensional, 0 dimensional, 0, 0. Okay, so everything matches. Now, the nice thing is we can always write the action in this form. Okay. So just using one of the 2 scalar superchargers, we can write the action in this form. So it's this bracket here just means the supersymmetry variation of that's generated by this guy acting on some kind of operator here, made up of the phi fields and the psi fields. Okay? And then you have some terms here which are, so this guy here, there is a metric dependence in this guy. And for convenience, we have written the metric as t times something, the scale factor times something. Okay, we've written it as t times something. And then we have the terms here, okay, the ellipsis here indicates additional terms which are metric independent. Okay, so they just depend on the complex structure, which means the metric is buried somewhere inside, but not explicitly. And then the Tn, this came from the pullback of the omega, if you remember. Alright, and why there's a T here, that's because the pullback involves also the metric. Okay, with the metric here, I mean the metric of the target space. Okay, so there's a metric here of the target space, and then you multiply it by T. Alright, so then you analyze this theory. Okay, you analyze this action. So you want to find the stress tensor, the components of the stress tensor of this action here. So you realize this, okay? So the stress tensor, the holomorphic component, which means the variation of S with the GZZ component of the row sheet, the metric. Now this guy, it's Q plus close. Okay, which means that if you take this stress tensor and act it on an operator to generate holomorphic transformations, it would change that operator to another operator which is still Q close. Okay, so that's what it means. So it means that this transformation generates changes to the space of operators that leaves it in the Q homology. That's what it means. But nonetheless, even though it's Q close, it is not Q exact. Okay, this is non-trivial consequences, and that's where this model is quasi-topological and not topological. Okay? In other words, it is non-trivial in Q homology. Okay, this is an important point. Now then you look at the other guy, the anti-holomorphic guy, so variation of S with variation of G Z bar Z bar. Now this guy is Q exact, which means it's trivial in homology, and we'll see why this defines a quasi-topological field. In a topological theory, both TZZ and TZ bar Z bar are Q exact. In other words, all components of the stress tensor are trivial. Okay? And in some sense, roughly, that means that no matter how you vary the action with whatever component of the metric, it's trivial. So the action doesn't change under deformations of the worldsheet metric. Okay? But in this case, it's not true. It's only non-trivial with variations to Z bar and Z bar. Okay, so this defines the quasi-topological model. So if you have a correlation function of operators inside, which are Q close but not Q exact, and then you do variations of that correlation function with the various components of the metric, only some of them vanish, not all of them vanish. So in that sense, it's only quasi-topological. Okay? So as you can see, when you put this guy in a path integral, which is e to the power minus s, it would localize or get you get main contributions from when this is minimum, when the action is minimized, and the action is minimized at points where it's Q plus fixed, meaning the variation of this is at its minimum, which is 0. And that tells us from these variations of the fields, setting them to 0 in particular, it tells us that this guy, the map, from the worldsheet to the target space, that's got to be a holomorphic map because del z bar of phi must be 0. Okay, very nice. So we have the right model that we want, that we can use Atiyah's theorem and then relate to everything else later on. If we had twisted a different theory, then this set of equations would look different, and if we were to set the variations of the fields to 0, it would be a different condition here. So in the other twist, which is like the B model, they call it the B model, you won't have a del z here, it's like a D. So it's like del z plus del z bar on phi equals to 0. Then that gives you a constant map. And so the moduli space in the path integral would not be the moduli space of maps, but rather just the target space itself, because a constant map from the point on the Riemann surface to the target space, the space of all those maps is the space itself. Okay, so but this is a different thing. It's the A model, so we have holomorphic maps, and this model is also the topological version of this model is also the one that is related to group-of-Witten invariance. Okay, so it localizes onto Q plus fixed points, and we saw that these are just holomorphic maps from CP1 onto the loop group. Very nice. Okay, so as we saw just now, the stress tensor, the TZZ, the holomorphic one, is Q closed but not Q exact, but the TZ bar Z bar 1 is Q exact, which means this. If you look at the conformal dimension operator, which is just the residue of the stress tensor, then it's trivial in the anti-holomorphic component, but non-trivial in the holomorphic component, which means that you can have observables which are state which have anti-holomorphic dimension 0, but holomorphic dimension 0 or more. Okay, so that explains that the Q-fast homology of the model has ground and left excited states, and the relevant operator observables O of holomorphic dimension 0 and positive are check homology classes of the sheaf. So this is a long story, but for the purpose of understanding, trust me, it's correct. Okay, so this thing here. Okay, so if you look at a regular correlation function of such observables here, okay, then you notice something very interesting, which is, now you look at this guy here. So you're summing over all possible maps, right? Path integral over all possible configurations, so all possible maps of n integer degree. And so if you look at this inside this guy here, now if you do a derivative with k, which is the scale factor of the target space metric, of this thing inside here. So you realize that it only picks up this factor, because there's only a t here. Okay? And then this factor gets picked up and comes down. And it comes down in this expression is basically just the expectation value of this guy. But for any supersymmetric theory, the expectation value of something, a supersymmetric variation of a field, that's 0. So you can see that this inside factor here, that's independent of the value of t. Which means that if we want to compute this guy here, we could just compute this guy inside for any value of t, and then put it back inside this expression for that, leaving this original value of t here. Okay? So this part is just non-perturbative, so it's a fixed value from the instanton, the worldsheet instantons, not the gauge instantons, the worldsheet instantons, and then you can just compute this in the large t limit, if you like. Okay? And why is the large t limit a useful limit? Because the t scales the target space metric, and the coupling of the sigma model is inversely proportional to the size of the target space. So if you scale it large, then you're working weak coupling, and then you can do perturbative calculations, and you're safe, you're good. Okay? So the whole localization program, in some sense, hinges on things like that, whereby you are just computing in the limit where something, the t is large, and then all you need to do is to compute the lowest order, and you're still good. Okay, so this is, in some sense, quasi-topological version of that. So this is how we compute the operators. Okay, so that's the quasi-topological sigma model. Okay, so let's talk about the kind of observables that we can get from this theory. So as I said, we have this target space, which is a loop group over, it's a base loop group. And so once the target space has some isometry, it will be inherited by the worldsheet. Because you have a worldsheet that's embedded in the target space. Okay? So the isometries of the target space will be inherited as worldsheet symmetries of the sigma model. So as we mentioned, this base loop group looks like this, and therefore we ought to have some kind of symmetry that's associated with the loop group SUK. And indeed, if you compute the local currents from the action, okay, if you compute the local currents from the action, we indeed get these J's which generate the current algebra of the loop group. Okay? So we have these conserved currents, that you get from varying the action and setting them to 0, the usual way, and then you compute them. What you do is you compute them by putting them inside here, like you compute these guys, like that. You get the currents, you compute them, okay, and then you end up getting, these things, basically. So these are OPEs, they really mean yes.
5 minutes.
Oh, sorry, okay, 5 minutes, okay. So, alright, so you get these OPEs, okay, like this, and then you can compute the OPEs together with the J's, and you get this. But okay, this expression here needs, okay, so, and then from these OPEs, you do the residue, and then you would be able to get this, okay, these commutators here, okay. And then in the dimension 0 case, this goes to 0, okay, so you can see this guy here actually tells you the conformal dimension, the holomorphic conformal dimension. When you put it to 0 here, the 0th guy here, this L0 operator tells you the conformal dimension. And so if you're in the conformal dimension 0 sector, it means M must be 0. And so when M is 0, then this guy here just collapses to this thing here. Okay, so we have like the topological sector having this, non-topological sector having this. But this is not the complete story, because the currents that we use in this computation were the classical expressions. Of course, the sigma model, it flows and there are some quantum corrections, and when you include the quantum corrections to the currents, and then you compute the OPEs, then you end up getting the toroidal algebra and FID algebra, as I mentioned. And these currents are in the Q homology. Okay? So once you have these currents, which are the Q homology, you then can construct states out of the expansion coefficients of these currents, okay, in the usual sense, creation operators on these states. And you can show that these states, again, are in the Q homology, Q plus close, but not Q plus exact, so they are in the spectrum of the quasi-topological model. And by the same time, we know that the quasi-topological model in the Q homology is given by this guy here. Okay, so this is a state, but nevertheless, with a conformal theory, with scale factor, the trace of the stress tensor being 0, and so this guy here would have a correspondence with an operator, which then has a correspondence with this check homology. So we have this here. Okay, and then using our Tia's theorem, we'll map this side here to this side here, basically. Okay, so and this means the following. So as I mentioned, the little strings, okay, the excited states are given by the check homology of the monad space of instantons, and that's given by the toroidal algebra. Okay, and so yeah, so okay, let me just hurry up, and then that's how we can get this. Okay, so there's some details in this, but that's the rough idea. Okay. Oh, and then we could prove this thing also. I sort of mentioned this in the Dong show earlier on in the talk. And okay, now the last part. So the M5-branes, the little strings that we're talking about, with type 2A fundamental strings bound to it as little strings, okay, that has an M-directed interpretation. Okay, so that descends from M theory actually. So if you look at M5-branes, okay, with M2-branes ending on them in one spatial direction as M strings, and wrapping the 11th circle of radius R in the other spatial direction of the M2-brane. And if you look at it at energies that are low enough, okay, such that the circle is small, then you actually have this little string description that is in the NS5. Which means if you're looking at the low energy regimes of the M5-brane with these strings ending on it, and low energy regimes that are sort of, and the BPS states which saturate the lower bound of energy, okay, then we could use the description of little strings to describe the BPS sectors of the M5-brane world volume theory, okay, and in the DLCQ framework. And if we do that, if you remember, so as I said, the ground state of little strings that describes the half BPS sector of an M5-brane world volume theory, and that involves modules of an affine algebra. You sum them up, then you get this character here, okay, of the affine algebra. Okay, so just to tell you some details here. So this is a character of the SUK module. This is a dominant highest weight, which labels the module. And then this is the complex structure of the M-string torus flow sheet, because we're using the LCQ, so you have a periodic direction, and then you're summing over all states, so you're taking the start and the end of the timeline, and then linking them together, so you have a complex structure of tau here, inside this guy here. So as I mentioned earlier on, it's a cousin of a modular form, and it transforms as a representation of itself 2Z. Now, how does this relate to 2, 0 on a flat space? So, this guy here, the torus that you see, that's made up of the circle in the space-like direction. So Neil was just talking about the LCQ, where you compactify the light-like direction, and then you do a boost, whereby there's this parameter epsilon that goes to 0. Now, if this space-like circle is not of 0 size, it means that the original light-like circle was decompactified. So really, even though we see something that has a modular symmetry coming from an apparent torus, we are really describing the theory that has no torus. So we do see an SL2Z symmetry in the theory of the flat space. Okay, so that's the point here. And then if you go to the polar BPS sector, which is described by the left-hand strings, then you will get this automorphic form looking thing. And that's in some sense like a stringy kind of duality, and that's because we have, if you look at this expression here, you have this thing which looks like oscillators coming from left excitations of a string. Okay, so that's the point. So we are really sort of probing the stringy part. Okay, really stringy part beyond, way beyond the 2,0 in these things here. Okay, so let me just conclude. I'm sorry for exceeding the time. Okay, so we've explained how a quasi-topological loop group model can be used to help us understand the 6D string, little string theory, derive and generalize this problem-applicable relation, understand the M5-brane world volume theory in terms of the BPS sectors at least. Notably, we find that the chiral spectrum of the little string is furnished by representations of the toroidal algebra, and the BPS spectrum of the M5-brane world volume theory are closely related to modular and automorphic forms. Consistent with these aforementioned physical results is the geometric length correspondence for surfaces, so it's all tied in, like you get all these results, but it's also correct with the math. And the problem-applicable relation and its generalizations, which we also physically derived. If you remember, we had the check one and the toroidal one. So we see a nice interconnection between string theory, M theory, geometric representation theory. This is what Langlands is known in from the math side, and of course number theory, because we have things that look like cousins of modular forms and automorphic forms. Okay, so it's a very nice interplay of these things. So what's to do next? So we have looked at just the chiral spectrum of the little string. Maybe we want to also understand the full spectrum, which includes the anti-chiral part, the right moving part. And that probably means that we would have representations of holomorphic toroidal algebra plus the anti-holomorphic part. Okay, so two parts. And then we would like to also derive the HED correspondence and its generalizations by gauging this sigma model here. Okay, and so what we would get is an equivariant version of check homology, not just the rank homology on the space of instantons, two toroidal algebras, W algebras. And finally, of course, we go beyond the BPS sector that we mentioned, the half and the quarter one. And we expect that if we compute this spectrum that's beyond the quarter BPS sector, we would get something like what we saw just now, just with an extra eta function that is valued in tau bar to represent the right excited states. Okay, thanks for listening.
questions now and postpone other questions to the coffee break. Isha, please.
Before invoking TS theorem, is there a motivation for why you want to look at moduli space of instantons on R4?
No, not really, because that comes from the DLCQ description of these things. So we start off looking at those because the end is to sort of use the loop group sigma model to describe it. So there's no prior motivation for looking at instantons and moduli space.
So there are no entities in that theory that look like instantons?
You mean what, on the loop group side? Or
no, like within the little...
Right. So yeah, I mean, it's limited to a DLCQ description of it. Yeah.
Any further questions? There's one.
Yes.
So I think Witten also has some derivation of this Baverman whatever correspondence.
Yes.
From just the
Yes, from 2,0. Yes, just purely 2,0.
So how does, but you need the whole Alice little string theory?
Oh, no. There are many ways to do it. Okay, there's the Witten way. There was my way, which I showed you, 5-branes. That uses, the M theory way was 5-branes wrapping on some kind of tab nut with the Riemann surface. I did some dualities to another M theory compactification, where the tab nut circle now, the number of centers gets swapped, and the asymptotic radius of the tab nut becomes small, and you compute BPS states in both frames, and since they are dual, the BPS spectrum should be the same, and then you get Ravelman triple work. Okay? That involves some work that you did recently for D4 and D6 intersection with the chiral fermions. Right. So the BPS states are all at the intersection of the D6 and D4. So that's the M theory story. So Witten uses a different thing. So he uses, well, I felt that when he described it using 2,0, it was not satisfactory. That was in 2008. I was there at the IS as a postdoc. He gave a talk on that. And I wanted to find a more rigorous way of understanding this geometric Langlands for surfaces, and that's when I used the M theory one. So there are many ways to get it, and from the little string now, using our TS theorem, we still get this identity. So the point is that this identity manifests in many different ways.
Couldn't you turn it around and say that actually you've derived a TS theorem from?
Well, actually, I thought about it. I mean, can we derive our TS theorem from that? Maybe, okay, I would say we would be able to do that because we really are just using this theorem and going this way. But an idea of how to derive this theorem would be something like this. I guess you start off with 40 angles, or maybe 2,0 in 6 dimensions, and then you have different compactifications down to 4 dimensions and to 2, and then you would get some kind of sigma model in 2 dimensions if you compactify down to 2 dimensions, right, in the usual Kapustin-Witten-Langlands kind of way. There was a series of papers in the 90s where people showed that if you have 40 ends of 2 super Young mills defined on 2 Riemann surfaces, you take one Riemann surface to be small, and you end up getting a sigma model on the one that is still large, and then you would have some kind of homomorphic map into something, and then so if you could sort of look at quantities which are invariant in terms of the sizes of these 2 products of spaces, and then have a sort of condition of a sigma model that involves the target space being a loop group, then you would have a TS theorem. I think it's maybe possible. I've seen some papers by, I think, Popov. I think there's this guy, I can't remember. He sort of has some relationship between, found some relationships between the Morris space of instantons and these maps. Yeah, so maybe along those lines. So yeah, so it's a nice thing to think about. We could probably think about how to physically derive a TS theorem.
Maybe there's some importance of getting coffee, so let's thank Meng-Chwan Tan.